So this is a practice question, again, referring to the different intermolecular forces. And here you can see that the alkanes, the strongest intermolecular force working on them is London dispersion. The ethers, right, they have that oxygen-carbon bond, and that oxygen-carbon bond has a dipole set up across it, so it is a dipole-dipole interaction. That's the strongest intermolecular force working on those. Then the alcohols and the amines both have hydrogen bonding, right? So these guys are H bonding. And recall that oxygen is more electronegative than nitrogen. And therefore, hydrogen bonding with oxygen is stronger than hydrogen bonding with nitrogen. So that explains the difference between all the boiling points and melting points we've observed. All right, so melting point's a little bit different, and I only bring this up because we got a good slide out of this, but melting point's a little bit different. Melting point doesn't only depend on intermolecular forces. I mean, it totally does depend on intermolecular forces. And if you have hydrogen bonding, that holds things together longer, right? So it takes a higher temperature to melt them than if you didn't have hydrogen bonding. But arrangement and crystal packing is really the other factor that's important to melting point. So remember that solids are nice ordered forms of molecules. And in order to get to a solid where you have a nice ordered form of a molecule, you have to have a nice clean packing of that molecule. Those molecules have to pack together nicely. So if you have materials that do pack together nicely, sort of smaller, more compact bundles, as opposed to longer, wigglier chains, right? The smaller, more compact bundles are going to stay solid longer because it takes more energy to break that packing of a nice, more compact bundle. So we have this analogy that we like to use, right? Think of snakes versus turtles. Snakes are like the long, wiggly chains, and turtles are like the small, more compact bundles. If you were going to try to put snakes in a suitcase or turtles in a suitcase, you would think that probably it'd be easier to put turtles in a suitcase because they wouldn't kind of squirrel around on you, right? And they would stay put for longer. It takes them a lot longer to get out of the suitcase to move around. So we used to use this analogy all the time, and then last year we found a news article where somebody smuggled a whole bunch of turtles in a suitcase, and we had to pull this picture. Right, this is a TSA picture where they found a whole bunch of turtles packed in a suitcase, and it was proving our point, right? Because it's easier to pack turtles in a suitcase than it is to pack snakes in a suitcase. Therefore, the snakes will get out a lot earlier, a lot quicker, at a lot lower temperature than the turtles will, because the snakes are wigglier and they don't want to pack like the turtles do. Now, the last thing we're going to talk about in this chapter is solubility. And in general, we're going to say that we're going to use this principle of like dissolves like. Things that are polar are going to dissolve things that are polar. Things that are not polar are going to dissolve things that are not polar. And here's my joke to introduce this to you. I've got the polar bear saying, "Help, help, I'm dissolving." The non-polar bear saying, "But bears are insoluble." And then the polar bear saying, "Well, that's easy for you to say, you're not polar." Ha ha ha, get it, because the polar bear is dissolving in water, which is polar, as we already discussed. It's a bad joke, I know. Anyways, basically what we're going for is things that have a lot of polarity are going to dissolve other things that have a lot of polarity, and things that are nonpolar will dissolve things that are nonpolar. So here's your scenario. You have a polar solute and a polar solvent. So here's my polar solute. It's composed of positive and negative charges, and they're all packed together nicely. And I bring in water, and we know that water has a dipole across it, right, with the positive side towards the hydrogens and the negative side towards the oxygens. That water can stabilize all the charges by having the negative side of the water pair up next to the positive side of the solute, and the positive side of the water pair up next to the negative side of the solute. And that's how you dissolve something like a salt, like sodium chloride, something like that. But say you have a nonpolar solvent. Now that nonpolar solvent with no charges set up across it is not going to be able to break the ionic bonds, right, between the positive and the negative charges. So the nonpolar solvent won't dissolve the polar solute because it can't break the ionic charge bonds, the polar bonds between the polar solute molecules. Now, say you have a nonpolar solvent and a nonpolar solute. Now you have really weak intermolecular forces, right? Probably London dispersion forces that are acting on both the solvent and the solute. There's no real tight bonds keeping these solute molecules together, right? Because all there is London dispersion forces, so that solvent can get in between the solute molecules and dissolve it. So it's easy to break those London dispersion forces that are holding the solute molecules together in this case. Now, if you take a polar solvent, right, the polar solvent won't want to dissolve the nonpolar solid or solute. And the reason for this is because the polar solvent has hydrogen bonding or strong interactive forces that are holding it together, and it doesn't want to disturb all of its hydrogen bonding by bringing some nonpolar London dispersion forces into the mix. So it would take, the polar solvent won't be able to break up the nonpolar solvent, mostly because doing so would decrease the amount of polar or ionic interactions in the solvent. So in organic chemistry, we're mostly worried about carbons and hydrogens, and we have molecules that have both polar components and nonpolar components. And we have really what's called this rule of 4. If you have 4 carbons, you're going to outweigh the polar component of an oxygen. So if you have 1 oxygen and less than 4 carbons, generally that's going to be soluble in water. And if you have 1 oxygen and more than 4 carbons, generally that's going to be insoluble in water. So carbons are going to tend to be nonpolar because they carbon-hydrogen bonds are nonpolar, so they tend to only have London dispersion forces working on them. So oxygens tend to be polar. More carbons, and you tend to be a total nonpolar molecule. Less carbons and more oxygens, you tend to be a total polar molecule. And it's roughly around 4 that dividing line is. Now, one thing we can do to really, if we want to mix organic and non-organic things, is to use something that's amphiphilic. And amphiphilic just means that it has a very strong polar group and a very strong nonpolar group. So carbons and hydrogens tend to be nonpolar. So this is an example of a fatty acid. It's got a large nonpolar group, and it's got a very strongly polar group. It's ionically charged, right? It's got a negative charge to it. It's very strongly polar. So what this will do is this will align in such a way that the charged part will interact with polar solvents like water, right? And the non-charged, the nonpolar part will align with things that are nonpolar as well, like oil or dirt or stuff that's organic based. And when you do this, you tend to make what's called a micelle. And so all of these charged polar heads, right, line up on the outside where the water is, right, and that water is interacting with the outside. And all of these nonpolar tails go into the middle, and they interact with each other, and they can dissolve oil or dirt or organic stuff in the middle, but still be carried away by the water because their polar heads are interacting with the water. So this is called a micelle, and this is really a microscopic bubble that you're forming when you wash your hands with soap and water. And this effect here is actually what's cleaning your hands right? Cleaning the organic compounds, or in recent days, what's disrupting the viral coat of a given virus that might be on your hands when you wash your hands with soap and water, right? This is what is cleaning your hands. You're able to dissolve nonpolar materials in water when you use soap. If we briefly go back to this acid-base mechanism, I just want to touch on this real quick. Now we can look at a couple of things, now that we know so much more than we did at the very beginning. I'm going to start with drawing the Lewis structures of the molecules that I have here. So now we know so much more than we did at the beginning of the chapter. We can see that this oxygen should have a negative charge on it. An O-Na bond should be an ionic bond. H and Cl is going to be a very polarized bond towards the Cl. And when we draw this mechanism, these electrons, right, on this negatively charged oxygen are going to be really attracted to the partially positive charged H. And when we end the mechanism, we're going to have a Cl with a negative charge, and that hydrogen is now going to be bonded to the oxygen, like that. So the polarization of the bonds is sort of dictating how the reaction mechanism is going to end up. Now, we're going to see this later, that we like to use these arrows to show what's occurring here. And this arrow is showing that this lone pair is creating a new bond to the hydrogen, and these electrons from the Cl hydrogen bond are going onto the chlorine, just like the polarization arrow would show us. All right, so we're going to see those arrows again in further chapters. But right now, let's just take a look at all the retrieval cues that we've gone through and all the critical skills. All right, so retrieval cues. Remember these ones, right? Valence electrons, those are the electrons in the outer shell of an atom. Lewis structures, we know how to draw those. Bonding patterns, those tell you charge, those tell you shape as well. Electronegativity, that's going to tell you the polarization of a bond. Covalent bonds are shared pairs of electrons. Ionic bonds are electrostatic interaction between two atoms. Sigma and pi bonds, don't forget sigma is head-on overlap and pi is side-by-side overlap. Dipole moment are those arrows that we drew for dipoles, right, or for molecules that showed the overall polarization of a molecule. Molecular geometry, we talked about that. Hydrogen bonding, dipole-dipole interactions, and London dispersion forces, those are all those intermolecular forces. And then hybridization, don't forget hybridization of orbitals. All right, so some critical skills. Acid-base mechanism, we're going to talk about that a lot more. Skeletal structures, being able to draw those structures without including all of the lone pairs and the hydrogens and carbons. Determining hybridization from shape, right, or from number of pi bonds, right, and then induction, doing electron withdrawing, showing electron withdrawing using those dipole arrows, and don't worry about electron donating. All right, so that's it. So we'll see you again in chapter 2.